Back again for part 2 of symmetry. Here's where we left off. We were talking about being able to recognize if 2 points were symmetric with respect to the x-axis. If they are, then their x-coordinates will be identical and their y-coordinates will be additive inverses. So that's with respect to the x-axis symmetry. With respect to the y-axis, you can recognize those points because their y-coordinates will be identical and their x-coordinates will be additive inverses. So let's try some. We're going to test this particular equation to see if it is symmetric with respect to the axes. First, we're going to see if the additive inverses change the value of the equation. Let's see, the value of the y, right? Let's see. Let's go back here and make sure we understand this. If we have 2 additive inverses for coordinates, a 2 and a -2, and the y, or the output of this equation, that's always the y, isn't it? If those remain the same, then we have 2 points that are symmetric with respect to the y-axis. So we're going to start by testing the y-axis right here. So I'm going to put x in, and when I put x in, a positive x, and I cube it, get my pen here, it's, of course we're not doing anything to y, and then I try, so that was what I started with, and what it's really asking me to do is this next one, to put in a -x and see if everything stays the same. Okay, if I put in a -x and cube it, is that going to stay the same? It isn't, is it? It is not. Then I'll have -x cubed. So not symmetric with respect to the y-axis. All right, so let's test it and see if it's symmetric with respect to the x-axis. And to do this, let's go back a moment. If we're interested in the x-axis, then we try the additive inverses, and we see if we get the same x, or whether it's going to change things. So I've got x cubed equals y squared plus 3. That's where I start. Now I'm going to try, see if it stays the same when I put in a -y and square it, of course. So I'm doing the squaring operation and then adding 3. Squaring operation and adding 3. What happens here? I end up with y squared plus 3. It stayed the same. It is symmetric with respect to the x-axis, yes. Now it might be interesting for you at this point to go ahead, oh, it's not going to be that easy. What would that look like if we graphed it? That's what we would love to see, wouldn't we? Put that on hold. We won't be doing that today. Let's test for x squared minus y squared. So we're going to replace the positive x with a negative x and see if everything stays the same. A negative x, and what am I doing to that? I'm squaring it, not doing anything to y. That's equal, sorry. And that does stay the same. Nothing changed. So yes, with regard to the y-axis, it is symmetric. Now let's try substituting in the y. Notice, please, that when we're looking for symmetry with respect to the y-axis, we're trying x and negative x. I'm going to go back again. Symmetry with the y-axis, we're looking at x and negative x. Symmetry with respect to the x-axis was y and negative y. That can be confusing. Let's try it. X squared minus, and now we're going to replace this with a negative y. We square it, and we look to see whether or not we're going to get the same equation. When we square a negative, we get a positive. So the answer is yes. This is also symmetric. So this equation up here is symmetric with respect to both x-axis and y-axis. The one we did earlier was symmetric only to the x-axis. When we put in the negative y, it worked. When we put in the negative x, it didn't. It was not symmetric to the y-axis. Equivalent equations have the same solutions. When a relation is defined by an equation, so we have some relationship between two variables, and we can write it up as an equation. Its graph is symmetric with respect to the x-axis only if you can replace the positive with a negative and get an equivalent equation. That's what we did just a moment ago. Its graph is symmetric with respect to the x-axis if and only if we can replace the positive y with a negative y and get an equivalent equation. In this one we just did, we have replaced the x with a negative x, and we got an equivalent equation. Our equation will graph symmetric to the y-axis. And we did the same thing with the y and found symmetry to the x-axis. Symmetric with respect to a point. So I'm choosing this point right here, and I can see that there's some kind of symmetry going on, isn't there? Some kind of symmetry going on. We've got this going down, curving back up, and over here we've got it going up and curving back down. This is symmetric with respect to a point. Do we have any capital letters which are symmetric with respect to a point? Well, the first one I think of is this one here. But there are others, and this one kind of suggests one of our letters, doesn't it? That one And see if you can think of any others which are symmetric with respect to a point. So for this second half of 9, when you come in, you're going to show me what you came up with. You can pause this for a moment if you want to take a minute. 2 points are symmetric with respect to the origin if and only if their x and y coordinates are additive inverses of each other. So in this case, we have to simultaneously put in the additive inverses. So let's try it. For this one, if I put in a negative y for the positive y, and at the same time put in a negative x for the positive x, will I have an equivalent equation? I would end up with negative y cubed, because remember, if this is odd, I retain the negative. And this one is odd too, isn't it? We haven't written it in, but we know it's a 1. So I end up with negative 6x, all equal to 10. Well, at first glance, it looks like this is not equivalent. However, I better take a second look. I've got a negative 1 over a negative 1. Negative 1 over a negative 1 is equal to a positive 1. So I end up with so definitely this was an equivalent equation, and this is symmetric with respect to the origin. Two points are symmetric with respect to the origin if and only if both their x and their y coordinates are additive inverses of each other. Exactly what we just did. We're going to try this one now and see if this one has symmetry with respect to the origin. Remember, we have to do these simultaneously. We're going to put in a negative x for our positive, and we're going to put in a negative y for a positive y. And we're going to see if we come out with an equivalent equation. This, of course, when we square this negative 1, we get a positive 1, so we get a positive x squared. And here, because we've got an odd exponent, we're going to have a negative y cubed equals 1. Is there any way that this can be shown to be equivalent to this? No. You could work on it a little bit if you want to convince yourself. This is where we're now going to define an even function and an odd function. We're going to start with the even one. A function is even when the value of the output remains the same whether you put in a negative or a positive. But we were just talking about that. What did we say when we talked about symmetry? Let me back up to here. Oh, that's good right there. A graph is symmetric with respect to the y-axis if and only if replacing x with a negative x gives you an equivalent equation. Replacing an x with a negative x giving you the same output. Well, that's true with parabolas, isn't it? I mean, if we had, let's say, y equals x squared minus 1. if I decide to put in, or let me write it with functional notation to be consistent here. So instead of writing y, I'm writing function f with an input of x. Now up here, I had equation y with an input of x. Functional notation just has me write this y differently. If I want to do function f with an input of negative x, I'm going to have negative x squared minus 1. And we know from the many times we have done this that this is equivalent. The output that we get from this operation is exactly the same as this output. So the output is the same. That's always true with an even function. An odd function looks a little bit different. When a function is odd, when I put in a negative x, my output is going to be a negative output. The sign of the input, the only difference it makes is it changes the sign of the output. So that's odd. Let's go back to even. The sign of the input does not affect the output. Isn't that weird? This doesn't make any difference at all to the output. But with an odd function, there is a difference. That the only difference is the sign. So it gets this nice kind of symmetry here. That's an odd function. Now, what kind of symmetry do you see here? Symmetry with regard to the origin, isn't it? Okay, let's try some functions. Here is where you should have your calculator ready. I should have mentioned that earlier. Pause for a moment and go get your calculator. It'll be so much quicker. Okay, you've got your calculator now. We're going to try a whole series of functions. And I want you to take a look at them on your screen. Make sure you've got you're going to go to y equals, and that's going to be your f of x. So this is the same as y, we know that. And then we're going to put in x to the first power. Now, if it is an even function, you're going to see it looking the same on both sides of a vertical axis. It's an even function. Oh, you know, I see a mistake on my slide here. Let me see if I can fix that. Sorry about this. Yeah, I've got these backwards. We know, we just read this, right? We know that it's not like that. Maybe this is a fortunate error. You might actually remember it better when you see me do this. No matter what we put in as an input, we get the same output. That's an even function. And in an odd function, when we change the sign of the input, it also changes the sign of the output. And we get graphs that look like this versus graphs that are symmetrical with respect to a vertical axis. Okay. So I'm back here. So what happened when you put in, let's try it, y equals x. Is that even or odd? This one was odd. And now try x squared, and what is that? That looks, when you graph that, it looked like this. I mean, I'm going faster than I should probably, but you can pause it. Okay, so if I erase this and go for, try that in your calculator, y equals x to the third. Odd, right? And now y equals x to the fourth, and that's even. So as you go down through these, playing with your calculator, you see that whenever you're raising this to an even power, you're getting an even function, and when you raise it to the odd power, you're getting an odd function, which is kind of neat. Isn't that neat? Oh, what's really neat is that we're at the end of our presentation. You can relax, and we'll see you in class tomorrow. Take care.